Okay, so continuing on formulation of the problem for the heated rod, this is a standard or staple example of how linear systems arise when solving differential equations. Okay? This is one example with finite differencing, which is pretty omnipresent. But in other solutions to differential equations, you will have constantly linear systems arise as part of the solving the problem. So the way they actually arise is that whenever we are discretizing the problem, so when I'm looking for the numerical solution, I'm not looking for the function that is defined everywhere. I'm looking for that solution function at discrete set of points. Okay. So your first step is to so-called discretize the domain. So here I have a heated rod. So it's really a one-dimensional problem. Do you see my mouse? It's kind of shy today. All right. So this is my heated rod, okay? And I know its temperature at one end, 40 degrees, and the second end, 200 degrees, right here. And the way to solve this problem is basically to figure out, okay, how many points in between do I want the solution at? And I added 4, x1, x2, x3, x4. So I'm looking for temperatures T1, T2, T3, T4, knowing T0 and T5. Okay? So I'm looking for 4 numbers, really. That's solution, numerical solution to this problem. Now, differential equation that governs the physics of this problem is given in blue over there. So it says that second order derivative in temperature plus H, which is something I know. It's a property of air around this rod and the metal, let's say it's metal, that the rod is made of. It's basically the transfer coefficient in between those two materials times ambient temperature TA, which I also know, minus the temperature at the point that I'm talking about, has to be equal to 0. So what really this says is that I would have certain dissipation of my temperature, but this contact between two different materials kind of involves a step function because they have different thermal capacities. Okay? So whatever the metal can deliver, air cannot necessarily receive at the same rate, which causes a step difference in the temperatures, so they don't equilibrate instantaneously. But I am losing some heat to that, and the rate of that loss is governed by H. So I am losing some heat to the environment. Otherwise, if this H was 0 and I had a completely insulated situation, then my solution would be really just, it would say d squared t dx squared equals to 0. Solution to that is a linear function. I don't even need necessarily a differential equation class to solve that. Okay? So it's simply a first order polynomial. And that means just a linear function between T0 to T5. However, that's not the case. It's not insulated, so I'm going to have some heat losses, and I want to predict how bad they are. Cool. So basically, what I need to now do is, at every of these points, x1, x2, x3, x4, where I discretized in between, I need to find an approximation to derivatives. So essentially, my approximation is given by second order difference, up there in red. So at any point, I can approximate second order derivative as t of x plus delta x minus 2t of x plus 2x minus delta x divided by delta x squared. So I can basically apply that at each and every one of those points. And I remind myself that if I'm sitting at point x1, then t of x1 plus delta x is t of x2, which is t2. Okay? So basically then, the difference is basically t2 minus 2t1 plus 20 divided by delta x squared. So that is my derivative. My mouse is really not following. All right. This is my approximation to the second order derivative by applying this formula. Plus h times ta minus t1 is equal to 0. When I clean that up, I basically get this formula. Okay? And I also understand that T0 is something that I have. It's 40. Okay. So I could do pretty much the similar thing for all other points. Okay. And I would get, so let's just see. So this is minus 2.04. Let me see if I continue. So this is minus, is this thing connected? No. I'm going to be there in a second. Okay. So this is minus 2.04 T1 plus T2 is equal to minus 40.8. Then if I did the similar thing with the second equation, so note that like I'm just going to write it in short terms and then I'm just going to show the cleanup version. Then I would have the same formula d squared t dx squared applied to the second point, which is t of x2 plus delta x minus 2t of x2 plus 2 of x2 minus delta x divided by delta x squared plus h times ta minus t of x2 is equal to 0. Again, I'm just replacing the actual derivative with the discretized version. What is t of x2 plus delta x? That's t3. So I'd have t3 minus 2, this is t2, right? And this is t1, and this is t2. And all the other numbers, delta x squared, h, ta, those are the numbers I have. Okay, they're given by the problem. So therefore, this is also a linear equation in t1, t2, and t3. Yes? So when I clean it up, I'm just going to give you the result. When I clean it up, I'm going to have t1 minus 204 t2 plus t3 is equal to minus 0.8. And I can continue. My third equation will actually have very similar structure. I kind of am just shifting with a similar type of discretization through these points. And I'm going to get T2 minus 2.04 T3 plus T4 is equal to minus 0.8. And then when I do the same thing at my T4 point, now I'm going to actually kind of reach T5, which is a boundary condition. And as such, it's known 200 degrees at T5. So I'm just going to place what I know on the right-hand side. And I'm going to get actually minus, or rather T3, no, wait a second, minus T4. Yes, T3 minus 204 T4 is equal to minus 208. So this increase in 200 is basically by shifting my T5 on the side of the things that I know. So basic step here is I have a differential equation. I first discretize my world, or I find the locations where I want solution to know the solutions. I will know the solutions, in this case, only at the 4 points I've placed in between. If I wanted more, I could place 40 or 400, but it's finite. Okay? Now, after that, at each and every of those points, my differential equation is valid. That's what governs, that's what's a result of the physics of the problem. And I just discretize that equation. And discretization means that I represent whatever differential operators I have. I use my values around me, and at every point I use the values around me to approximate second order derivative, first order derivative, whichever one I have. And that gives me, ultimately, when I write that down for every point where I'm looking solution at, that gives me a linear equation in the value that I'm at and maybe surrounding points. But 3 or 4 at most, depending on how wide is my what we call stencil or the numerical operator. Okay? And then I get like a structure like this. This is basically when I actually write it down as a system, you would get something like that. This minus 2.04100. 1 minus 2.410, 0, 1, 1, 0, 0, 1. Again, I get this a kind of banded structure that is moving through. What do we call this type of system? Does anybody remember practice exam for exam 1? Tridiagonal. It has 3 diagonals that are 0, and it's zeros otherwise. So my main diagonal has minus 204 on it, and the other 2 diagonals have 1s.
For line 4, when you have that T3, is that a positive or a negative? I can't tell you.
That is a positive, sorry. I didn't erase it. There we go. And then on the right-hand side, I have minus 40.8. Okay. If I had more points, this system would look the same as it was just larger. Okay? And what would change is that delta x, so the numbers would be ever so slightly different. I wouldn't have 0.04, I believe I would have, it would scale with delta x. Okay? So it just gets larger, but I can basically write it down in a consistent fashion. And then the other side has this, most of the elements are the same, I just have boundary conditions 40 and 200 appear as part of it because those are my known points. Okay? This is very, very common in differential equation, these types of systems. And consequently, so knowing how to solve either tridiagonal or pentadiagonal systems is important. Questions? Question? From my last time, I wrote that down. But I did actually go over it. Oh. This was my first. Okay? So I did write it down today. Okay. And then I continued. Okay? So this is my number 2, actually. Yeah. So your little quiz assignment for this time, for next time, not for now, will be to actually type this system in, solve it, using either your Gaussian elimination or the solver that we have in NumPy, and plot the solution. Yeah, that's 4x4.
Use Gaussian.
Whatever it is that you'd like to use, and solve for T1, T2, T3, T4, and then plot the temperature profile for this rod. Okay? So I'm going to create that assignment when we get home. Again, just typing it in and seeing the solution.
So how did you get equations 2, 3, and 4 again? Just, like when you said T1 minus 2.0 plus T2 plus T3.
So basically, that differential equation that I have, that's what's guiding the physics. And then instead of d squared t dx squared, I use approximation for it. And that approximation looks like this formula here. Where is it? Mouse, hello. Okay. This one. This is my approximation for second order derivative. This approximation links neighboring points. So if I put x1 here, then this is x1 plus delta x is x2. Okay? So second order derivative at this point is value here minus 2 values here plus value here divided by delta x squared.
I can't see where you're pointing on the screen.
This big red thing up there, right? Place x1 in there and go to the plot.
Okay.
The approximation for second order derivative of t at x1 takes value at x2 minus 2 values at x1 plus value at x0 divided by delta x squared. When you substitute x1 for x in here. Mouse is just not, and this is, I'm tall, but damn, I'm not that tall. This one over there, right?
In the red equation.
And I'm glad, I'm tall plenty enough, I don't need to be taller.
The red equation was approximation.
Yes, so the red equation saying central difference for d squared t dx squared, that's the approximation for derivative. So approximation for derivative, you designer, you're given, hey, use this approximation for derivative, and that's how you go and discretize a differential equation. Very important for your upcoming computational project. You're going to be given a differential equation important for reservoir simulation and get to discretize it. But what I will want you to do in that project is to figure out the rule how to change discretization at the vim. So I want to say, hey, I want 40 points in between, do this. Or hey, I want 400 points. Can you write the system that is 400 by 400 without writing everything line by line? So a little portal to create your system. Okay? Because that's what we want that flexibility. Hey, if I change delta x, what's the improvement that I get? Yes?
So for the quiz specifically, you want us to solve like the numbers on the bottom using Gaussian?
Yes, I want you to actually do this 4x4 system that I wrote at the very end.
So basically like number 3 on homework?
Number 3 on the homework, I don't know. What is number 3 on the homework, Ningyu?
And that's a negative 40.
Use any solver you'd like. You can do Gaussian elimination that we worked with, that we programmed ourselves. Or you can do NumPy's linout.solve. Again, the means of solving is not the point. Just take a look at it. See how different it is from that linear. I'm going to formulate a little problem. So I want you to appreciate how different this problem is, or this solution is from actually just drawing a straight line. Okay? Okay. And remember the process because you're going to use it in your computational assignment. All right. Let's now move on to one more part that we're going to review, actually, how you do something called LU decomposition by hand, so that I can ask you to program, of course. So, and programming it is actually going to be much shorter than doing things by hand, because programming it is only a small variation in Gaussian elimination. So let's get going. This is, the topic is called LU decomposition. I think I'm getting whatever my husband has. Okay. LU decomposition. But I would like to use a subtitle for that. It's called Solving Multiple Systems with the same A. And by that, I mean AX is equal to B. So this LU decomposition is one of the ways to save time. Now, I think the exercise or the quiz question that we had last time around has proven to you that solving a linear system can take a moment, okay? And depending on the hardware you have, well, it could be 2 moments, you know? It could be a little longer. So we want to be more efficient when solving the system. So first thing that we can do is simply be smarter, okay? So if I'm going to solve a lot of system, and often, so this previous problem that this tridiagonal system that we got, if I wanted to resolve that problem with different temperatures as the boundary conditions, my main A, that tridiagonal matrix, would remain the same. Okay? The only thing that would change would be that right-hand side, that B. Right-hand side, sorry. My right-hand side is on your left. So we had AX is equal to B, and those coefficients in matrix A were kind of static there with the problem and material properties of the problem, like H is built in there and how I discretize the system. But the actual temperatures, T0 and T5, they actually appear on the right-hand side. And if I wanted to change T0 and T5, I would just change that right-hand side. So if I wanted to test how this heat transfer is happening for 70 different temperatures, T0 and T5, different pairs, okay, I would go and solve this system 70 times, and the only thing that I would change is that side B. This happens actually often, because just the way we are physically setting up the problem, boundary conditions go to that right-hand side that is known, and most of the rest of the material properties of the system, such as the heat transfer coefficients and so forth, they're actually just hanging out in my coefficients matrix A. Okay? So if I'm not changing those, I'm actually not changing A in itself. So in physical model, just before, in model for heated rod, we ultimately got a matrix system AX is equal to B. Note, if I changed T0, T5, those are my boundary conditions, temperatures, only B would change. Therefore, if I was tasked to actually see, as an engineer, to see what's happening for all of these different temperatures, because you solve something for one temperature and the weather changes outside, of course, and changes the temperature that is surrounding your problem, right? So in that case, you might just need to slightly change your system, but not quite, right? So if you're tasked as an engineer, most of the time you're going to be tasked as like, well, solve this 800 times and optimize something. Tell me something what is physically happening with the system and how can I actually improve it. That's the task of an engineer, right? So how do we speed this process up, right? So technically I could be tasked to change T0, T5 multiple times. multiple times and calculate heat losses accordingly, for instance. In which case I'm solving AX is equal to B. I'm going to call this B1. AX is equal to B2. And so forth. AX is B, well, N times or something. Or M times, I don't know. So question is, can I then, so if my, what was the average time? 1,000 seconds? For that, I didn't calculate average time, but let's say that it's 1,000 seconds. Actually, I calculated it and I forgot it. Okay? I looked at it on Friday and forgot. So 1,000 seconds, let's say, for that system that is 10,000 by 10,000. Okay? So if I need to solve it 70 times, that's 70,000 seconds, right? Can I cut this in half, say? Yeah, that's a good question. And the answer is yes. So there is something that we can actually do while we are solving the method and record, and then just every time boundary conditions change, it actually makes a difference. So let's actually, we will do that in a second. I will give you one more example where this would be beneficial. So I'm just trying to motivate first the problems. Save. Another problem would be actually finding an inverse. When finding an inverse, we're looking for A inverse matrix such that A inverse is the same as A inverse A and is equal to identity matrix. Remember that? Now we can actually pose this problem as solving linear systems. Look at this. Let's say that this matrix A is represented as A, and then I have three columns, x1, x2. I'm going to work with 3 by 3 example. So if my inverse is a matrix, that matrix has 3 columns. So I look at those 3 columns as 3 unknowns, okay? 3 unknowns. Then this is the same as, if I actually do matrix multiplication, this is the same as AX1, AX2, AX3. And if you don't believe me, we'll do this multiplication and convince yourself, yes?
When you have like x to the 1, does that mean a column?
It's the entire column. It has 3 values. Okay. And if I did the matrix multiplication, what would I end up having? My result would be 3 columns, or matrix with 3 columns, such that first column is actually AX1. Okay? Well, that has to be equal identity, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. So solving or finding this inverse is equivalent to solving AX1 is 1, 0, 0. AX2 is 0, 1, 0. And AX3 is 0, 0, 1. Mm-hmm.
Why didn't you consider that 9 unknowns? Or
Because this way it's just shorter. This way I'm going to have...
you're splitting the columns.
I want to fit it into a certain mold that I will be able to use. So this is this mold where I have A, X, that I'm solving for, is equal to B, and my B is the only thing changing. Do we agree? So this is 3 by 3. That's easy peasy. I can do that by hand, and yes, you will do that by hand. But in general, my matrix could be much larger. Okay? So this could be a 10,000 by 10,000. So I would solve this 10,000 times. Smile. Times those 1,000 seconds. We've been here waiting till Christmas. Okay? So basically I have 3 systems with identical matrix A and only right-hand side RHS B changing. So this is another example where I might have multiple systems with the same coefficient matrix A, and then just changing right-hand side. Go. So the way we're actually going to shortcut this is to perform our, remember that forward elimination step, okay, as we were doing Gaussian elimination. I was doing forward elimination. I created an upper triangular system based on this forward elimination. And then we actually introduced B, okay, as the right-hand side and did back substitution, though I was changing B as I went along. Okay? So technically, I can do this. I can modify my forward elimination slightly and record coefficients of another matrix, which I'm going to call L, and split A as A is equal to L times U, where L is lower triangular matrix and U is upper triangular matrix. And I do that, basically it's equivalent to doing that forward elimination. Once I have that, then I can, every time I get new B, all I do is this back substitution step, give or take, of some sort. Okay? And that can actually cut the problem in half, in the sense that this LU decomposition, this first forward elimination, was quite massive, was half of that time of 1,000 seconds. Right? So if I do that once and repeat only the second half, I have already saved quite a bit of time, especially if I'm doing this 10,000 times. Okay? So that's essentially where we're going. And now I'm just going to prove it to you that this somehow works, and this will inform our procedure. Save. So basic idea, do forward elimination only once. And in that process, find LU such that A is equal to LU. And this is upper triangular matrix, and this one is a very specific lower triangle. There's no one way to do this, just like there's no one way to do those manipulations in forward elimination. But as long as I figure out how to do this, I can proceed. So my example would be A is 1, 1, 1, 0, 0, 0. And then I have, so 1, 1, 1 is on diagonal of this lower triangular matrix. Let me just write this down if you don't mind. So this would be my matrix L. And the upper triangular one is U11, U12, U13, 0, 0, 0, U22, U33, U23. And the key will be is that this U is actually what we get as an outcome of my forward elimination already. I just have to kind of record my coefficients L, and I'll be done. Okay, to be continued on Wednesday. I hope you can wait till Wednesday to find out the result.